Testing. Give it up again because they didn't hear it. Yes. Hi, I'm Natalie. I am so happy we are halfway through the series, which is kind of sad, but we have a really special presentation today. We're going to be talking about FM synthesis with Uche and John Chowning, one of which is the inventor of FM synthesis, and you'll just have to stay tuned to see who it is. And so Uche will be demoing it, and then we'll watch the interview with John Chowning. Again, we don't know who the inventor is yet, so you'll have to stay tuned. So let's give it up for Uche.
Okay, I am just going to start with a demo here. Let me make sure that everything is set up and get started. This here. Cool. All right. So I'm just going to play through something that I've already sequenced, and it's songs that you might know. So I'd wonder if anyone can actually get it. So I'm going to start now. All right, so did anybody know those songs? Yes, no. All right, it's great for me. So those two, if you didn't know, were two songs from the 80s. One was Take On Me by AHA, and the other one was Kenny Loggins' Danger Zone. And they both used this particular electric bass preset from the DX7. So you might be asking, Uche, what is a DX7? Glad you asked. So it was the first popular digital synth. It would have costed you around $2,000 at the time, but it was severely under-manufactured in that Yamaha originally planned to produce 20,000 units, and it sold around 200,000. And the presets on it, because it was notoriously hard to program, basically defined 80s pop music. In fact, you can actually still hear the sound today. Let's see. So, does anybody recognize this? Taco Bell sound. So you might be wondering, why am I even mentioning this 80s synth? All of the sounds on the DX7 were synthesized using FM synthesis. So what is FM synthesis? In general, I'm going to put in context of all the kinds of methods of synthesis that we've been talking about so far. So we have, and we've got where we will go through these kinds. So we started with additive, then Nico showed us subtractive synthesis. Then we have wavetable synthesis, sampling, and then we will, in the next lecture, go over physical modeling. These kinds of synthesis can be kind of split into three different categories. You have compositional synthesis, where you're taking elements of sound and trying to add them together, whereas you have decompositional types of synthesis, where you start with something relatively complex and try to cut out the excess. And you have existential, where you're trying to copy something that already exists, either by like copying the literal samples that you can record from the sound, or trying to model how it physically works in order to produce the sound. FM synthesis would fit under compositional synthesis, where you're taking bits of sound and trying to add them together. For these kinds of synthesis, you generally want relatively simple waveforms, just so that you can kind of control what exact sound you'll end up with at the end. So how does it work? Just ignore everything else that I'm going to say today. It's just really, really, really fast and broad. So in the process of FM synthesis, we start with some kind of output for your audio, and we have some kind of simple waveform. We're going to use signs. Signs are commonly used for this kind of synthesis. Then we have a way to control the amplitude of that sign, and then we wrap it in a bow with some kind of pitch input for that oscillator, and we call this an operator. And this essentially is what is producing sound in FM synthesis. But it wouldn't be FM synthesis without some kind of modulation. So we can copy an operator and hook the output into our pitch input to control the pitch of this operator. And to get some terminology out of the way, we can call the operators that you can hear carriers, and the operators that are operating on another operator modulators. In this relatively simple, like two operator structure, we only have one modulator, but you don't have to stop there. You can have more and more modulators. You can connect as many modulators as you want, theoretically. And this entire format with its connections is called an algorithm. Because we're routing these to each other, you can actually control that algorithm, and using the same number of operators, you can have different algorithms to produce different kinds of sounds. So FM synths are generally categorized by two things, which is how many operators do you have total, and how can you route it? You have a fixed algorithm FM synths where the routings are predetermined. You have a certain set of them, and you can switch between them freely. And then you have free routed FM synths where you can control the routing manually. So to talk about how FM synths actually make their sound, this is just in the frequency domain. You can talk about FM synth as adding harmonics to your spectra in multiples of your modulating frequency. So if you have some carrier at some frequency F0, you can say that when you modulate it by if you modulate using an operator at a frequency F of M, then you'll have sideband frequencies at F0 plus and minus K by FM, where K is just an integer from 0 if you're referring to the carrier to infinity. So in FM synths, you can actually generate harmonic and inharmonic sounds using the relation between these two frequencies, where if they have a rational relation to each other, then you'll end up with a relatively harmonic sound, even if it's not necessarily consonant, but that's more subjective. And if the relation between the two frequencies is irrational, then you will end up with a purely inharmonic sound. So the actual amplitudes of the sideband frequencies that FM synth adds are governed by these things called Bessel functions. So your carrier's amplitude and kind of phase essentially is determined by the zeroth order for first kind Bessel function, your first set of sideband frequencies. So at F0 plus FM and F0 minus FM would be controlled by the first order, and so on and so forth. So I've been calling the input to an operator a pitch input specifically because of the realities of how pitch is controlled, in that the DX7 and most FM synths, they operate using something called linear FM, where the frequency input is modulated in hertz in frequency, and whereas you can also modulate something using semitones pitch, because that's how in like modular synths, how a pitch is expressed is using voltage that's mapped onto semitones. The problem with just directly doing that, though, is that pitch is a logarithmic scale. So, logarithmic scale. So, a constant increase, so like increasing by 12 units, would double your frequency, which introduces problems when you're trying to have a certain pitch when you're frequency modulating. So for example, if I have a carrier at 440, if I'm using linear FM, I can say I modulate that by 100 hertz. So then I'd start getting sidebands at 340 and 540 hertz, right? Whereas, and the center pitch would be 440. Whereas if I'm expressing it using like linear degree, like linear unit or exponential units using notes, I would say, like, for example, I'm going to modulate this 440 pitch up and down 12 semitones. That becomes 880 and 220 hertz, where the center pitch becomes 550 hertz. So you start losing their sense of pitch once you start modulating using exponential FM. And I'll show both today. So we get to have fun. So, okay, so I'm going to switch us to something that can show us like a oscilloscope and a spectrum. So we start off with a sine wave, right? There's your nice little sine. So when we start modulating it, this is a linear FM synth, so you're going to just see the spectra, those harmonics start to be introduced. And of course, you can modulate our modulator. So, that's our modulator modulated. It's kind of hard. So if I turn out our modulator, we just get our sine back. But if I turn back our modulator on, you get our modulated modulator. And when I was talking about see. So we can go from, we can actually directly hear what was modulating our modulator here, just a sine. And here we go, back. And of course you can have you can hear you can hear something that's being both a modulator and a carrier here, where you're hearing this modulator here. So you can kind of still see the sign. Well, it's hard, but let's see. Then start doing that. Then we can just go through some exponential synthesis. So I just have a sine being controlled by another sine here. Right, and we get our sine wave again. So then I'm just going to start modulating. This was what I mentioned. It's easier to see if we can look at the spectrum, where we start. Notice how it starts drifting out of pitch as we modulate it more and more, because this is exponential. We're modulating by semitones. Yes.
What exactly
The units of notes. I was asked what exactly is exponential in this. It's because pitch does not have a linear relationship with frequency. It has a multiplicative relationship with frequency. So if we're modulating linearly by pitch, we will multiply the frequency, which will create an offset from the pitch that we're expecting. Yeah. So, okay, let's see. So that's, so if I go back to slides, okay, this is just something, a short kind of interlude that I need to do. So there's this other instrument called a Casio CS101. It came out around the same time as the DX7. Some music use this. Is this FM synthesis? This does not use FM synthesis. It uses something called phase modulation. And then you might ask, why am I talking about phase modulation? Some cases, phase modulation can be used to emulate the sounds of FM synthesis. In the case that you're modulating only like sine waves, and your goal is to do linear FM synthesis. This happens because when you're doing frequency modulation, you are modulating your frequency with some function, whereas when you're doing phase synthesis, you are modulating your frequency by the derivative of some function. And in the case of a sine wave as your modulator, these are related by phase shift. So you can get similar sounds. So just to show that, I'll go back and just show that real quickly. So we can do and we get kind of the same sounds as we did when I was doing linear frequency modulation earlier, but this is phase modulation. So, okay. That was my presentation. Are there any questions? Yes.
What's
in those songs. So that for that, you start actually wanting to get like some kind of like transient or like noise sound, right? So in that case, you actually start using self modulation. So uh, let's see, I can actually kind of show that. Oh, sorry. To get the kinds of sounds that the DX7 used for like the bass, how do you do that? And how you do that, to at least get like the initial transient, like that sounds kind of like plucking a string, you start wanting to get like something that can be inharmonic, even if you can, even if you only like relate the frequencies to each other in a relatively harmonic, in a relatively rational ratio, in a rational ratio. And in a way that was done was through self-modulation. So if we feed this back into here, you start getting that noise, and then you start controlling it with envelopes in FM synthesis to kind of get that pluck sound. So I can kind of show that. Here. And you can start building up the sound from there. Any more questions? I'm using phase modulation because there isn't actually a linear modulation input here. I could actually do frequency modulation, it would just be out of pitch. Question? Yes. How common is frequency modulation? A lot of the difference between like DX7 and a lot of our tools now. Oh, sorry. I was asked how common is FM synthesis now, and I'm saying that the difference between like the DX7 and now is that now we have like the computational ability to combine a lot of these processes. So even if something isn't like just using signs to modulate frequencies with each other, you can actually hear it a lot in stuff like, if you've heard dubstep bass, like from Skrillex, that a lot of the times uses FM synthesis to get a harmonically rich starting point for subtractive synthesis, where you start cutting out like the pieces that you don't want. And it's just mostly like a lot of modern music techniques are combining a lot of these synthesis techniques with each other. Are there any more questions? Yes.
So, was there some kind of reason that FM synthesis was like easy or like a natural thing to do?
Was there a reason? I was asked, was there a reason that FM synthesis was an easy or natural thing to do? And you'll probably see in the interview, but FM synthesis kind of falls out of a concept that's like relatively common in like stringed instrument for unfretted stringed instruments, where you start like wobbling the pitch. You can actually I can actually demonstrate it really quickly. So if you have some pitch input, and you start modulating it very slowly, right? It wouldn't be like to this degree in the actual stringed instrument. It would be like relatively gentle. So you'd get like so this is just vibrato, right? And you can take that process and make it really fast, and then just this will go out of pitch because I'm using this input, but you can start increasing the frequency that you're using vibrato at. Let me expand it. See. So, yeah. So then you start producing sideband frequencies. Any more questions? Do I know? I programmed those two at the very beginning. I started with it. Yeah. I was asked, do I know any popular hooks? And I said I just programmed it. All right. Question? Okay. So we have an interview with the inventor FM synthesis.
Me. Just kidding. Let's give a hand to Uche. So yeah, we'll be playing our interview with the inventor of FM synthesis, John Chowning, who we interviewed, I think, Tuesday of this week. He is 90 and thriving, as it seems. He invented FM synthesis in 1967, and it was first used in a musical instrument in 1973, but the DX7 was invented, like Uche said, in 1983. So Prince's When Doves Cry, It Has Take on Me, George Michael's Careless Whisper, all of these have the DX7, which is just like, oh, Tina Turner's The Best and Smooth Operator as well. I'll use the DX7. So it's extremely important and wasn't recognized at the time of invention, but at a bit later. So we'll play the interview for you now. Let's give a hand to the...
What was the path to, when you were training as a composer to being, such an early pioneer in kind of computer music?
Yeah, so I studied in Paris for 3 years after I did my military service during the Korean War. And I went to college, and then after college, I went to Paris to study with a famous teacher at the time, Nadia Boulanger. And I spent, basically 3 years there. And while I was there, I heard music that was intended for loudspeakers. Remember, in those days, all music that we heard was either TV music or music recordings of orchestras or chamber music or whatever, or bands where the intended source was not the loudspeaker. That was the way they communicated. But when I was in Paris, I heard music by Stockhausen where the intended source was the loudspeaker. And that was very exciting. I heard a piece by him called Contacta, which was based upon 4 channels, 4 microphones on the corner of a square table. They used a rotating loudspeaker in the center and put a single channel into the speaker, rotated the speaker, recorded the 4 output channels from the 4 microphones on a 4-channel tape recorder. So that really got my interest. It was, and I imagined doing similar things, but maybe not just circular motion, but more extensive kind of spatial trajectories, distance and angle. And so when I finished my studies with Boulanger, I went to Stanford to get a degree. They had no interest in this kind of music, and there was no interest in electronic music, tape music of any sort, which is not unusual in those days for an American university. But I talked, I played in the Stanford Symphony, and the percussionist next to me was a biologist. And of course, timpanists and percussionists, they have lots of rest, so we had lots of time to talk. One of the things that I talked about was the fact that I'd heard this music by Stockhausen in Paris. And one day she came up, 1963. She handed me an article by Max Matthews at Bell Labs, his first publication of the idea of digital domain, doing music with computers. Of course, these were big, batch processing computers. And so I read the article, contacted Max, and then he gave me a box of cards. And so I had never even seen a computer before. My whole training was music. My interest was music. I was not a ham operator. I had no technological background. But in this article, there was one diagram which showed a computer, a digital analog converter, and a loudspeaker. And I thought, well, if I can learn to program a computer, then maybe I can bypass all the complexity of analog synthesizers that I knew about from Stockhausen's work at Cologne and Berio's work in Milano, others. And so I took a program course, learned to program, and that was the beginning. So I worked on spatialization beginning in 1964 at Stanford with long distance help from Max Matthews. And one of the tuba player in the orchestra, tuba players also have lots of rests in orchestral music. So he saw me I knew him just as a tuba player, a really good one. When I brought these to, and he said, "And help you," it turns out he teaching TA for John McCarthy's course in Lisp, or AI and Lisp. So he helped me, taught me everything I needed to know to get going. And he basically became my angel. So in 1968, I had a fully developed spatialization program with Doppler shift, Q4 channels, etc. But along the way, I discovered FM in 1967. And I was looking for a signal that would distinguish itself from the reverberant field. So a direct signal which has a little change in pitch will separate itself from the collection of reflections, reverberation, the echoes, and the direct signal therefore can be distinguished from the reverberant signals. And so I was experimenting with vibrato. I had studied, as a child, I had studied violin. Excuse me. And so I then just kept playing with vibrato, deeper and deeper, faster and faster. And pretty soon I heard something that was surprising with two oscillators. I heard a complex wave that I knew would have taken probably 10 or more oscillators to reproduce. So that was the kind of moment when I realized, okay, there's something that's beyond the ear here. And so that's the whole beginning. That was the beginning of FM synthesis. So it was a musical discovery, an ear discovery. It was not a discovery of mathematics or engineering, because I had no background there. And so I always like to point that out, that in all the years, my best tool has been my ear. It's the last thing that I rely on to tell me whether things are right or things are wrong. How does it sound? Which is perception. So a lot of my work had to do with, over the years, had to do with perception.
Did you say you when you learned the program, it was with John McCarthy?
Yeah. I took a course
On
in Algol 60, which was in the day that was thought to be the language of the future. McCarthy was teaching Lisp, because Lisp was his language. And we had a Lisp, we also had Lisp eventually at Karma. And I programmed some in Lisp, but the original language was Algol. Then from that I learned the SAIL language, Stanford Artificial Intelligence Language, which was an Algol-like language was designed and implemented by the guys at the AI lab. So I was a early morning, late night user. I was not allowed to work during the day because I was not funded, but Dave Poole convinced McCarthy that this was an interesting project. And so over the years, music became one of the more interesting demonstrations that they gave at the AI lab, in fact. These super engineers, this was the Sputnik era. So the DoD gave tons of money to McCarthy and at Stanford and MIT, his colleague, forget his name, but anyway. So these were really the best of the best as far as computer scientists, engineers, speech. Raj Reddy, for example, at Carnegie Mellon, and he was one of their researchers. And they taught me a lot. And I learned a lot from them. And but they really kind of watched as we built this quite extraordinary music system.
Well, that's amazing. That's an amazing person to learn from. McCarthy, also a hero of mine. I was lucky me and Nico got to see him speak in 2008, just a few years before he passed away. He obviously coined the term AI. I remember him saying that he just hoped that people continued to remember the importance of learning about logic in building thinking systems, which was a very affecting thing on me and Nico. That's very cool that you learned Lisp from him. I heard when you were at SAIL, you guys built the first online computer music system. What did that entail?
It was not real time, but it was a single pass system. But we had to write the output of the music program onto disks, and then when the computation was finished, then we recorded it from the disk direct through DACs, 4-channel DACs onto 4-channel tapes. So that was our system. Then eventually we got the Samson box, which was a real-time real-time signal processing computer highly optimized for doing music. And the Samsung box was probably produced more hours of music than any other single device ever until the DX7 maybe.
When you started experimenting with increasing vibrato frequency until you got to the point that you were producing, audio band interactions and complicated timbres, how quickly did you kind of realize the flexibility of that method?
Pretty quickly, one of it was a long night. I began and I had to wait for maybe 10, 20 minutes between each, say, 1.5 or 2 second sample, because this was a time-shared machine. So if the rate at which my samples were computed depended upon the number of users. But anyway, one of the things that I realized that at the end of this long night, I had made the deviation, that the depth of the modulation just made a linear change from 0 to big. So that meant that basically sweeping the modulation index, although I didn't know those terms. For me, it was frequency deviation or vibrato depth. In fact, that's the way I was thinking about it. Those were the terms in my head. So I thought, okay, vibrato depth from 0 to something, and what I heard was a diphthong, like ooh, ooh, which we know if we sweep the index from 0 to something 4 or 5, that's what the sound that we would hear. So I thought, well, this is amazing, because there's no way anywhere on any device in those years where one could produce a diphthong, which of course is essential to speech.
Yeah.
And so then I developed the idea of resonances, like all these, the vowel resonances based upon Johann Sundberg's work. I developed a model for the singing voice, FM model. And that was very successful. And all of this, of course, was licensed to Yamaha back in 1972, 73. And they worked for what? The X7 was 1983. So they worked for 10 years before they had a real winning product. But they had foresight.
Did Yamaha consult you much as they were
Oh,
building?
yeah.
They
Yeah,
did,
yeah. I went
Japan.
to Japan maybe, I'm guessing maybe 8 or 10 times. And I would spend a week or 2 working with their engineers, explaining to them what I had learned. And they would listen to the changes I made on their real-time system, which was a PDP 8 or 5 or some small PDP computer with a breadboard implementation, but it was real time. At that time, we didn't have real time at Stanford, and so that was a lot of fun for me. And it was very interesting to be able to hear in real time, make changes. And that was pretty exciting. So they would listen and learn how I was hearing. So these engineers, maybe 50 or so over a period of 10 years, they're really the ones who are responsible for the DX7. I became the face of the DX7, and I always recognize them publicly, that it was really about 100 really good engineers over a 10-year period to whom that DX7 should be attributed.
Once the DX7 came out, it was pretty rapidly adopted across the entire music industry. What did that feel like to just hear FM synthesis sounds just appear everywhere within like a year of that technology finally coming to market?
Well, that was not my world. That was all mostly pop music, and
Right.
I didn't know much about it. But what I was very happy about was the fact that the DX7 democratized computer music. Until the DX7, you had to have a multi-million-dollar system, and but then the DX7 with one of the early Atari or a Apple and the opcode system software, you had a pretty powerful workstation, and that's when Dave Bristow and I wrote a book about programming how to use the FM theory that was published by Yamaha. I forget the title exactly. I think it was FM Theory by Musicians for Musicians, something like that. And Jean-Claude Risset and I began writing a book about based upon the DX7 on perception, being able to demonstrate certain phenomenon, lots of phenomena. For example, missing fundamental phenomena, or resonances, all sorts of things that could be done. But then Yamaha in those days, they didn't, as soon as they had a new instrument, then they would stop support of the original one, DX7, the original DX7. So the people lost interest, and we never finished it, unfortunately.
The DX7 reminds me of a question that we're always facing with, like when you're doing product engineering versus just inventing, there's always a trade-off between complexity and features and something that actually be adopted by the public. Today, we're trying to build bots that, small businesses can, talk on the phone for them, and these are not technical people.
Right.
The DX7, I've only used an emulator of one, but it's very complicated to design the algorithms and understand what the effects are going to be.
Yeah.
I'm very curious, what was the push and pull between like complexity and being able to achieve really complex sounds versus something that was like simple enough that could be used in this like major Yamaha consumer product?
Well, the cartridge had a very special attribute in that it was a read-write cartridge, and it would write in a few seconds. So what happened, people would plug in to write what they had done on this cartridge, would go into their pocket, they'd pass it to a friend who would copy it. The friend would end up in Singapore the next night and pass it to another friend who would copy it, and then that person would make modifications, and it would end up in Paris, 2 days later. And this was an amazing kind of metamorphosis of a single patch that would occur through time and through space, that really few people understood what would happen if you had, for example, 4 operators in a stack, and they all had different frequencies and different modulation indices and offsets. It was just too complicated. But there were some interesting sounds that were done. and they are preserved in these cartridges, and they were modified and used all over. The way I work is I have a basic unit of three modulators and 2 carriers, and the 3 modulators can be used to emulate resonances in the singing voice. For example, if you have the carrier frequency at 3 times the modulating frequency, and the modulating frequency is F sub 0, the pitch frequency, then you get at a small index, you get a nice bump, filtered, looks like a filtered, you know, sawtooth wave or something. And so this is the way this is where I build complexity out of using numbers of these piled on top of other. So a single sound may be 4 or 5 of these all occurring together, each one contributing to another part of the spectrum. That's very easy to control. And so that's the way I build complex tones with FM synthesis.
When, you first were implementing FM synthesis, offline in a non-real-time manner, and then, eventually you said at Yamaha, they began to have a real-time version of it running in software. In the interim, there was a long, almost a decade between, those 2 periods. Was there motivation to try to reproduce those sounds using analog oscillators and muxes, or was it always a commitment to try to implement it using digital signal processing?
We never had an analog device in our studio.
Really?
Never, no. They were too unstable. And the whole richness of the DX7 and as a workstation was that you could reproduce exactly in one location because it was digital domain. And Buchla tried to make FM, but I explained that you can't do it because you're working in log space, changing voltage, and FM is based upon a linear space. So although he tried, it doesn't work. Simple, just plain and simple. It doesn't work. Plus the fact, if it did, it was so unstable you couldn't count on it being the same sound the next day, because the analog systems were so sensitive to changes in temperature, but primarily probably.
I mean, I know that in the early days of computer music, especially with so many classically trained composers like you as early pioneers, there was a large emphasis on trying to reproduce the timbre of known instruments. But over time, it became increasingly a focus to also invent new sounds. Do you think when you first were working on FM synthesis early, a lot of your focus was on trying to reproduce sounds like, chimes that were hard to produce, with other methods? Or were you, as a classically trained composer, also interested in new sounds that you couldn't produce with other synthesis methods at the time?
Both.
Both.
Yeah. I mean, one learns a lot by trying to synthesize a sound that one knows well. For example, when you're succeeding, when you're close, and when there's something about the sound that's missing, so you have a target, and having a target made a huge difference. Jean-Claude and I both worked on synthesis of of well-known orchestral sounds, just because we learned so much about perception, like the voice synthesis. That was one of the richest experiences of my life, is succeeding at creating female and male vocal tones, sung vowels. And because I learned so much about perception. But if you listen to my pieces, like Stria or Tyrannus, these are sounds that we'd never heard before. Boulez gave an introduction to Stria at the Théâtre d'Orsay in 1983, I think. And he said that there's nothing in this piece that I recognize from my tradition, but he really liked it. And so that was, and that transcription is of his talk is on my Karma website. So if you look at Karma People, Chowning, you'll find a website, you'll find a lot of the Boulez's transcription. And it's a very interesting long commentary about Stria.
I'm really curious what you're excited about now, what presently, anything.
Yeah, I'm working on a piece for Lisa Moore, who's a very fine New York pianist, for disc clavier. And because my hearing's not so good any longer. And this is a piece, I want the pianist just to have a real keyboard, because she's a concert pianist and specializes in new music, but she also plays the standard repertoire. But I want her to have a real action of the piano. But then I'm going to, because it's a disc clavier, you can mute it and turn off the acoustic sound. And at some point I will substitute an FM piano and then do things that have some unusual theoretical basis, which I would have to have diagrams to explain to you in a short time. But anyway, it's not so ear dependent. So it's something I can do, which is really exciting for me.
All right.
Yeah.
Well, I think
Give me a
thank you so much for your time. Really appreciated it. So
You're welcome. My pleasure. We inspire one another, right?
we try our best.
Yeah, that's the whole thing. Those who inspire become inspired and inspire others.
Thank you for coming. I will leave this up here. Anybody who wants to come and play stuff on DX7, feel free to play. Let's see. Oh. There we go. Yeah, it's
Cooper I have something for you. This is the piano ones. Yeah, do you want to hear it, Cooper? That's some. I haven't told.
Oh no. I'm so triggered.